Hi guys, welcome back. If we can start with some green check marks, please. Hopefully everyone had a relaxing, enjoyable break. And you're back, ready for action. Before we left off on the break, we had just finished up Unit 10, and I had requested that you submit your Unit 10 material, and that way you could have written the test. Now, there's a few of you who have yet to do the Unit 10 material, which needs to be done yesterday, actually about 2 weeks ago. But anyways, so Unit 10 is done. You should have your Unit 10 learning guide submitted. You should have written the Unit 10 test, because today we're moving on to Unit number 4, kind of going backwards. So we're going to start the chemistry stuff. Units 4 and 5 and 6, 4, 5, and 6 are all chemistry. And then the last 2 units, or last 1 unit maybe, I think 4, 5, 6, and 7 are chemistry. Anyways, we have a bunch of chemistry in the next few weeks, and then we move on to the physics unit last, and that's kind of it for the year. The end of this term is on April 19th. That's the last day of term number 3. And on April 20th, I believe it's a Thursday, we're going to have our first midterm exam. So April 20th, I sent out that email yesterday to you guys, but just in case you didn't read it yet. April 20th is a Thursday, 9 a.m. here at McWilliams Center. The test, last year I said it should take an hour. It took a little bit longer, maybe like an hour and a half. So just plan for that on Thursday, April 20th. What's going to be on that test? Everything from Unit 1, 2, and 3, which was the biology stuff. And then we did Unit 10 as well, which was the earth science. So Units 1, 2, 3, and 10. And then we might get through Unit 4 prior to then, the chemistry stuff. So there will be for sure a little bit of chemistry on there. I don't know exactly how much, just kind of depends on how far we get. So you're looking at the biology, the earth science, and a little bit of chemistry on that midterm exam on April 20th. So half of the material we'll cover this year, essentially. Does anybody have any questions on that? Don't remember how many questions I put on it. Mainly multiple choice. There are a few short answer questions in terms of chemistry naming and things like that, which we'll look at in the next few weeks. So that's that. Nobody has any questions about the midterm exam? Anything about Unit 10 stuff that should have been done? Any questions, concerns, anything that you were unsure of? If nobody, is it multiple choice? Yeah, mainly multiple choice, a few short answer for that midterm. So mainly multiple choice. There we go. Hopefully you guys received that email I sent you yesterday. I asked you to print off the Unit 4 learning guide, and I want to go through Unit 4 in the next little bit. Now, the Unit 4 material, there's a lot of stuff that you've already seen before in different science courses. Like I've just finished up with my grade 8s. Well, I shouldn't say just before Christmas we finished up Bohr models in chemistry, and literally like the stuff that we do in grade 10 you've learned in grade 8 already. I haven't taught grade 9 for a long time. I don't remember exactly what that looks like because they have changed the curriculum, but you've definitely seen a lot of this beginning chemistry stuff, especially from Unit 4 before, which is a good thing. But Unit 4 and chemistry in general, it's kind of, I don't want to say it's like math because it's not number oriented, but when we start doing this chemistry, the stuff we learn at the very beginning kind of builds, and then you need that stuff to learn the next stuff, and then you need that stuff to learn the next stuff. So if you don't have that foundation, the Unit 4 stuff, when we get into balancing and acids and bases and types of reactions, if you don't have the foundation, you're going to find it really difficult. So for those of you who like to, fall behind and then catch up all at once, you have a really, really tough time with this chemistry. So my recommendation to you is, and I mean, this is always a recommendation, but is to go through the stuff each day. Dedicate an hour each day to science. And I mean, an hour like outside of class. You probably won't need that much at the beginning, but as we move into the material, you probably will need it. And we'll go slow and I'll answer all the questions you have, but it's really on you guys to kind of keep up with what we're dealing with in class. So let's just take a quick look at Unit 4 here. We've done Unit 1, Biology. We've done Unit 2, 3, and lost my cursor. Scroll down a little bit here to Unit 4. So there's a bunch of stuff kind of hiding in here that you won't have to worry about right yet, but we have atomic theory and bonding, which we're going to cover today. Names and formulas of compounds is kind of possibly the first new stuff you'll encounter, so that'll likely be on Thursday. You'll notice that I have a few extra practice sheets in here, so like naming extra practice and counting practice. So we'll go kind of through those together. I don't think the learning guide does a great job of this unit. I think that in general chemistry, it kind of just breezes through it like you just see one example and know how to do everything. So I like to take my time. We'll go a lot slower. We'll spend a long time doing Unit 4 here, probably the next month. So this definitely isn't like biology. We're just kind of go through it. We'll spend lots of time on it. And that's chemistry stuff. So we're going to just jump into it. Now, Costin, you asked, when is it due? What are we talking about? When is what due? The unit. 10, 4, 1, 2, 3? Which unit are we talking here, Costin? Unit 4. Well, it's due when we're done. I mean, it takes as long as it takes us to get through it. So Unit 4 will likely be due May sometime. Possibly at the end of April, but I doubt that we can make it through it that fast. So yeah, definitely a while to get through Unit 4. Not like, in the biology units, we've been doing a unit a week or a unit every 2 weeks. We're going to spend a lot of time on this stuff just to make sure we're all with it. So we're going to go through the learning guide like we always do. We bounce around a little bit. I don't like the order that the learning guide's in. So in the notes here, you'll see, go to the bottom of page 4. It's not actually the bottom of page 4. It'll be different for everyone depending on your printer, but we do bounce around a bit. So this is at the top. We start at the beginning, the top of the Unit 4 learning guide. And then I'll tell you when we kind of need to go to a different page. And then we'll go back and we'll figure it all out. So atoms join together to form compounds. This is something you likely already know. So an element is a pure substance made from one type of atom. We're going to talk a lot about the periodic table, and you should definitely have a copy of the periodic table with you. You'll need it almost every day for the next month or so. So oxygen, it's one type of atom. We can make a molecule of oxygen if we stick 2 oxygens together, O2. Compounds are also pure substances, so we can have a compound like salt, like table salt, sodium chloride, made up from 2 different atoms. So we take sodium, we take chlorine, we stick it together, and we have a compound. So oxygen, hydrogen atoms, H2O is water, it's oxygen, hydrogen stuck together. And the chemical change occurs when the arrangement of atoms and compounds change to form new compounds. So if we have water and we introduce some electricity to it, it'll break down into hydrogen and oxygen, but it's going to take a lot of energy, and that's chemical change because we're using like electricity to break something down. So we can change compounds to form new different things. We can break bonds, we can form bonds. These are all chemical changes. And you spend a lot of time in grade 9 or I think 7 actually, talking about the difference between a chemical and a physical change. Does anyone remember what some of the indicators of a chemical change are? Anyone remember that? Chemical changes, or the definition of a chemical change, not the like definition from, you know, the internet, but just what is a chemical change? Nobody remembers the difference between a chemical change and a physical change. All right. Yes. Heat. All right. Chemical changes, typically heat is created. That is a great example of something that happens in chemical change. Basically, chemical changes are difficult to reverse. Sometimes we have heat, light produced, new colors possibly. Those are all kind of the big ones for chemical changes. So, atomic theory, atoms are made up of smaller particles known as subatomic particles. I haven't taught grade 8 for a really long time, and we just started, or we didn't just start. Before Christmas, we were working through chemistry, and you have to learn about quarks in grade 8 these days. Did you guys learn about quarks when you were in when you were in grade 8? The different flavors? I don't know when the curriculum changed, because it did. I don't know if you guys are like, if you missed the change or if you experienced the change. Nobody remembers. All right. When you guys were in grade 8, you possibly learned about quarks, which is kind of funny because when you make it to grade 10, we don't talk anything about quarks. We just talk about protons, neutrons, and electrons. You'd maybe remember quarks. The flavors, 3 flavors, they have different charges, 2/3, negative 2/3. Nope. All right, there you go. Anyways, protons, neutrons, electrons are made up of quarks. And you don't need to know that apparently because you're in grade 10 this year. So protons, P with a plus sign next to it. It's just a symbol we use to describe what a proton is. Neutrons, an N with a 0 next to it because it has no charge. And then electrons, a little E with a minus sign next to it because it has a negative charge. The protons and neutrons exist in the nucleus. You have an atom, the nucleus, the middle is where your protons and neutrons are, and then the electrons kind of buzz around the outside. And we kind of think of like a typical model of an atom having this nucleus and these like electrons kind of orbiting the outside, kind of like the solar system, when it's not actually what atoms look like. These electrons are going so fast they exist in kind of like a cloud. So you think of like a fan, either a ceiling fan or if you have a fan in your room to cool the room down or circulate air. When the fan is stopped, you can see, you know, 3 blades on a fan. But when you turn the fan on, those blades are going so fast, you can't really see where the blades are at any one point. And that's kind of the way you want to think of electrons when they're orbiting. They kind of exist in clouds because they're going around pretty quick. You can't really tell where they are at any one time. There's kind of everywhere, nowhere at the same time. Relative mass is possibly a difficult concept to kind of understand. Basically, if we gave an electron a mass of 1 what, you're asking? Not 1 kilogram, not 1 anything, just 1. Just 1. That's what an electron weighs. It weighs 1. Then a proton and a neutron would weigh about 1,836. So electrons are very, very small. It would take almost 2,000 electrons to make up a proton and a neutron. So there you go. That's how small electrons are. So we can talk about the nucleus. That's the middle. This is where the protons and neutrons live. And then we have the electrons buzzing around the outside in what we call shells. And in grade 10, we just say they're just basically the 3 shells you need to know in grade 10. Once you make it to grade 11, you learn about some other different shells and different shapes and orbitals. Now, there's some, I guess it's kind of vocabulary, atomic number, atomic mass. It's very, very common for students to mix up the atomic number and atomic mass. And electrons exist in the space in shells. The number of protons is the number of electrons in a neutral atom. So we're going to talk a little bit about atoms and ions coming up here. And the atomic number is the number of protons. So this is why it gets so confusing, because we give different names to the same thing. We say, okay, you have atomic mass, and that's the number of protons and neutrons. And we say we have atomic number, well, that's just the number of protons. And then we have the nuclear charge, and that's this. So it's kind of confusing because we just have multiple names for the same things. So the atomic number is the same thing as the number of protons. The really cool thing about your periodic table is that on your periodic table at the top and the middle, we'll look at it in a second, you have this legends that's right down beside me here where this titanium is. And the legend tells you what each number is on each little box on the periodic table. So the number 22 is the atomic number, and that's how many protons an atom has. The symbol, the name, the atomic mass is protons and neutrons combined together. And then some atoms will form ions and have a charge. So the charge will be indicated there. Some have more than one charge because you get into these funny situations, different orbital shapes and whatnot, which you won't learn until grade 11. But for now, you just need to know that sometimes atoms will form ions. So what do you absolutely positively need to know? You need to know that the number of protons defines an element. If you have 3 protons, you're lithium. If you have 8 protons, you're oxygen. If you are oxygen, you gain a proton somehow, you're no longer oxygen. Now you have 9 protons. You're a whole new element. You lose a proton, now you're no longer oxygen, you've lost one. Gone from oxygen down to nitrogen. So the number of protons defines an element. If it gains extra protons, it becomes a new element. If it loses protons, it becomes a new element. There we go. Periodic table, you guys have seen it, you know it, you love it. Maybe you don't love it. You've seen it, you know it. The periodic table is just one of these amazing things. It is organized in so many different ways, all in one chart, and there's trends and things going on. It's just amazing how organized the periodic table is. I don't think there's anything like it in science, where things are just kind of organized so well. So generally speaking, we have elements listed by atomic number. You start at 1 hydrogen, 2 helium, 3 lithium, 4 beryllium, 5 boron, carbon, nitrogen, oxygen, fluorine. Each time you go up, you get a new element. The metals are on the left, non-metals are on the right. Kind of have the metalloids in the middle, the transition metals. There's a staircase. That's kind of a dark line we'll look at in a second, and that separates your metals from your non-metals. You can see it over on the left side of your table there. I guess that's the right side of the table, sorry. There are rows, so it's important to know the difference between a row and a column. A row is called a period, a column is called a family. And different families have different properties, and if you exist in a column, everything below you exists similar to you. That is for groups 1, 2, 17, and 18. So the first 2 columns and the last 2 columns, those are the families. You have your alkali metals, your alkaline earth metals, the halogens, and the noble gases. Wouldn't it be great if that was just written on the periodic table? Yeah, it would be great. And it is. So when you get to a test and it says, the halogens are blah, 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 and you're like, oh, halogens, I've forgotten what the halogens are. You just go to your periodic table, boom, bottom of the periodic table, the halogens. Done. Noble gases, alkali metals and alkaline earth metals. So those are the 4 big families, all labeled on your periodic table. All right, so this is it, periodic table. I obviously have a nice colorful version. When you guys do your final exam and your midterm exam, you'll have this nice colorful version as well. You can see the families are here. The first green columns are going up and down. Like at the bottom it says alkali metals. Next family over, you have the alkaline earth metals, and then the on the far right here, the halogens and the noble gases. You can see that the metalloids, the transition metals in the middle, are blue. You have the non-metals in the top right corner of this orange color. And obviously you guys have seen the periodic table before, so there's hopefully no surprises here. This is the exact one under your data booklet. You'll see that it has this nice little legend here at the top, so you can see what everything means, what the numbers represent, things of that nature. Does anybody have any questions about the periodic table? No? The periodic table is really quite interesting. Technically, the periodic table has these two bottom rows, and you can see how there's this kind of line where they should be put in the middle of the periodic table here. The lanthanides and actinides, that's what we usually call them. So the periodic table really should look like this. But that's just way too big to fit on a piece of paper. So what we do is we take the 58 all the way across to 70, and then 89 all the way across to 103. And we kind of take our scissors and we cut them out, drop it down, and then squish the periodic table together. So if we kind of go back, if we look at the numbers, you know, everything's organized by atomic number. When we get down to the bottom here, we get to 56, and then we get to 57, and then it goes to 72. Well, that doesn't make any sense. Everything else is in order. I mean, we had like up here 39, then 40. If we go 57, and then we drop down 58 all the way across to 71, and then we continue on with 72 here. So that's why those two rows kind of float down there at the bottom, just because if we had everything all together, the periodic table would just be too big. So just so we can get it neatly on a page, we cut out those two rows, drop them down to the bottom. Really, they should be in the middle, like that. Just recently, after this periodic table is published, if you go on the internet and look up the most recent versions of the periodic tables, there's some elements kind of behind me here, 112, 113, 114. These have all been named now, 112, 113, 14. They just had kind of generic names before, and then they've been named after people and people who discovered them and places and things of that nature. Number 2, Jenna, it's a great question actually, and leads, you're all over it. You can see how hydrogen's kind of goofy up at the top here. You have number 1, hydrogen, and then you go to the other side and you're like, oh, here's hydrogen again. Why does hydrogen get to exist at 2 spots on the periodic table? That's unfair. Nobody else gets 2 spots on the periodic table. Why is hydrogen special? We'll learn that coming up. Does anybody know? Know why hydrogen's special? Hydrogen's a bit tricky, and we'll look at a little bit more in depth, but hydrogen sometimes behaves like a metal, so it wants to be on that left side. And then sometimes hydrogen behaves like a nonmetal, so it wants to be on the right side. So just depending on how hydrogen's acting, sometimes it acts like a metal, sometimes it acts like a nonmetal, and it can be on either side, just because it acts like a metal and sometimes not. Helium is number 2, which Leeds pointed out, which is over here on the top right corner at the top of column 18. So because that first row kind of looks a little bit funny where hydrogen's in kind of 2 spots, but the first row really is hydrogen on up here, and then it goes all the way across, and then you got helium on the far side. And then you go down, and then you get to lithium, which is number 3. You restart again, and then 4, and then you kind of skip across, and you get to 5, 6, 7, 8, 9, 10. And then you go back to 11 and 12, and then jump across to 13. It's not until you get right in the middle, where you have 19, 20, 21, where things kind of line up again. But really, those should be separated, and you should go from 19 and have that big gap, kind of like that, 19, 20, and then jump over to 21. So the periodic table is a bit funny sometimes, but it's amazing how everything's just so organized, and we'll look at it. All right, so this is where we're kind of going to jump around a little bit. We've talked It says the bottom of page 4. I printed off a learning guide yesterday, and it was actually like the top of page 5 for me. But Bohr model. Can somebody maybe just fire it into chat what page Bohr model's on for you? Just depends on how your computer's formatting the PDF file. It might move it to a different page. Yours is on 5? Is it on 5 for everyone? All right, so the first time I printed it, it was on page 4, but now it's on page 5. All right, so we're going to jump. I can just change it right here. We're going to jump over to page 5, and we're going to talk about Bohr models. Has anyone never talked about Bohr? Who has seen Bohr models before? That's probably a better question. In either grade 9 or grade 8? Yes? Okay. I mean, I have to teach it to you anyways, and I will, and it's really important. So we're going to definitely go through it. Is there anyone who doesn't recall ever seeing Bohr models? And this is kind of a Bohr model above my head here. Is there anyone who just is like, you know, Mr. B, I've never seen a Bohr model before? The dots and the numbers in the middle. Not like you don't remember it, but just, yeah, you've probably never seen it before. There's no shame in it. We'll spend lots and lots of time looking at them. It just kind of lets me know, yeah, what we need to do and cover and not cover in depth. So I can maybe spend a little less time on Bohr models because you've likely seen them before. So Bohr model, Niels Bohr was a guy, I mean, you spend a lot of time talking about it in grade 8, even probably in grade 9. Different people, you know, about 100, 150 years ago, had different ideas of what atoms look like. Because we can't physically see with a microscope an atom, it's just too small. All we can do is just kind of, you know, estimate what things are doing there. So basically, Bohr models show us where the electrons appear, and it shows that they exist in these things called orbits or shells. We'll talk about them in terms of shells. And in reality, electrons can kind of jump around from shell to shell, especially the outer electrons. And really cool things happen. But you won't learn about that until you get to grade 11 and 12 and university. So from now, we just talk about the electrons where they lie, and then the outermost electrons are kind of the important ones. So each shell has a maximum number of electrons it can hold. We'll talk about the first 3 shells, and then when you make it to grade 11, you'll talk about the rest of the shells after that. Now, when we draw a diagram, just to make everything nice and neat and organized, we draw everything as circles. But in reality, these shells are 3-dimensional. They're kind of spheres, not just like a circle. So the electrons aren't just going around in a circle. They're going everywhere in a big sphere. Just imagine that. And the most important ones that we always talk about are the valence electrons. And valence electrons probably possibly a new term. And valence just means the outermost electrons. So the ones that are in the outside shell, the last shell, are the kind of the important ones because they're the ones that determine the reactivity, what that atom's going to react with or not react with, things like that. So there you go. Now, does anybody remember the rules for the shells? How many go in the first shell? How many go in the second shell? How many go in the third shell? We only have to do the first 3 shells in Science 10. Do you remember what those are? First, second, third? 288. Got her, Eric. So yeah, in grade 10 we only need to know up to, well, sometimes we go past 18, not very often. Never have to worry about the 4th and 5th shells. All right, so we're gonna, I don't know why I put this in here. I meant to put this in. Looks like it went in the wrong spot. All right, this was supposed to be right after the first periodic table. Might as well look at it now it's here. Then we'll talk about the Bohr model for a second. So this is a periodic table, and if you've ever wondered kind of what elements are used for, we have a use for almost all the elements, even the kind of the unstable ones. And I just found this the other day, and I thought, well, I might as well look at it. So I don't know. What's cool here? Things that I didn't know. I think it's cool that if you look at the last column, the noble gases, helium, neon, argon down the far right side of the periodic table. They're all used in lights and lamps because they're really stable. You can give them some electricity and they produce light, which is pretty cool. Even some of the really weird elements down at the bottom that we don't have a lot of in nature. Neodymium magnets is neodymium. That's pretty cool. Those are some pretty crazy magnets. Things like color TVs, fluorescent lights, a lot of medical stuff and like lasers with some of these elements because they are so specific. So we do have a use for almost all of the elements on the periodic table, except some of the ones that don't exist for very long. There we go. All right, so this isn't in your notes, but you might want to just jot it down as just possibly a reminder, or you could just, just write a note 288 on the side of your page or something like that. These are kind of the rules for Bohr models. So if you didn't remember, like Eric did, how to draw Bohr models, we're going to spend a lot of time looking at them, but just we should have some ground rules, and these are the rules that I will follow always when drawing Bohr models. So in the very middle, in the middle circle, we're going to write down how many protons the element has and how many neutrons the element has. That way we will know exactly what we're dealing with, and that'll become very important as we move through the chemistry unit. So number of protons goes in the middle, number of neutrons goes in the middle. Those are the first two things we're going to do. And then we're going to talk about electrons. We're going to start in the first shell. That's going to get 2 electrons. So we'll draw 2 dots. And then once we fill that shell up, we go to the next shell. And then we draw another 8 dots, possibly. If that gets full, we go to the next one, has another 8. So we go 2 and 8 is 10 plus another 8. We're going to be mainly dealing with elements 1 to 18 in drawing Bohr models. And then it asks us to try to draw the Bohr model for an atom of oxygen. So you probably have some room, maybe on the back of your learning guide or wherever, if you have a spare sheet of paper. You likely haven't drawn a Bohr model in a long time. So let's draw a Bohr model of oxygen just to make sure we can do that. So if we had a periodic table, and I have a feeling we do have a periodic table handy, we could look up oxygen. We can find oxygen on our periodic table. Here she goes. Thank you, Mr. Ross. You can see that oxygen is up there in the 16th column, the second row. It's number 8 on the periodic table. And we know that the number of the atom, or the atomic number, is the same as the number of protons. So it's number 8. And it has an atomic number of 16. So that'll become important here in a second. So I'm just going to maybe just draw it. Here is what oxygen looks like on the periodic table, 8 and 16.0. It has a charge of -2 if we need that, but we don't. So that's kind of an abbreviated oxygen from the periodic table. So when we draw the Bohr model, in the very middle, we write down how many protons we have. I'm going to put a little line. And how many neutrons we have. So we're always going to put that in the middle. So the atomic number is the same as the number of protons. So this should hopefully all be a review. Atomic number equals number of protons. And in oxygen's case, that is 8. All right. The next thing is the atomic mass, which is the number of protons plus the number of neutrons. So if we add the protons and neutrons together, we get the mass. Now, why do we call that the atomic mass? Well, basically if we had an atom, the protons and neutrons are about 2,000 times as heavy as the electrons. So we don't really care about the electrons. If we have a bunch of protons and neutrons, the mass of the electrons doesn't even matter because they're so small. So we want to know how much an atom weighs. We say, okay, how many protons does it have? Those are heavy. How many neutrons does it have? Those are heavy. We take those two heavy things, we add them together, and we get the mass. So the thing with the neutrons, you probably remember from doing this in grades 7 and 8, 9, is that to get the number of neutrons, you have to subtract the number of protons from the atomic number. So number of neutrons, n with a little 0 next to it, is equal to the atomic mass minus the atomic number. So in this case, our atomic mass is 16, and our atomic number was 8. So the number of neutrons, 16 minus 8, is 8. All right, so when we want to draw our Bohr model, we have the number of protons and the number of neutrons. And again, the number of neutrons is just, we know the atomic number is the protons. That's what makes an element an element. We know the mass is the protons and neutrons added together because those are the only heavy things in an atom. So if we know how many protons we have, we know that the mass is 16, 8 of those are protons. What's left? Well, 8 left for neutrons. Okay, so we've done our middle circle. I apologize for those of you who are like, Mr. Borden, done these Bohr models so many times. All right, so there's my circles. The next thing we need to do is establish how many electrons we have. Does anybody remember, just in general, the rules for electrons in Bohr models? How we come up with the number of electrons? Costin, how can we find you? Do you need a map? GPS, perhaps? Atomic number, number of protons. Ah, wasn't meant to be that funny. Are you with me on atomic number, Costin? We can take a second to talk about it. I'm sure there's other people who are lost as well, Costin. It's not just you. Atomic number. That's where you lost. All right. We can help you get found. I'm just going to jump over to our fancy dancy periodic table here. So at the very top of the periodic table, it says atomic number in general. So this one element here at the top in the middle, Costin, is just an example. It's a kind of like a legend for the whole periodic table. So the atomic number is the number in the top left corner of each and every element on the periodic table. The atomic number is the number of protons. They are one and the same. I could cross out atomic number and write in number of protons, and they would mean the exact same thing. Now if we look at oxygen in that top left-hand corner, just above my head here, oxygen has the number 8 in the top left-hand corner. And that 8 up there just means that oxygen has 8 protons. That's what oxygen defines oxygen. If you had 9 protons, boom, you're fluorine. If you have 7 protons, boom, you're nitrogen. The atomic number we're focused on, so you're getting me mixed up here. Kyla, you're right, but you used the wrong word. Yeah, it's 8, not 16. So the atomic mass is how much the thing weighs. If I asked you what your mass was, you'd go stand on your scale and you'd look down, you'd be like 100 and something pounds, and that would be your mass. If I took an atom and I put it on a scale and I said, how much does that atom weigh? Well, they're so small, it doesn't make sense to talk about the mass. You don't need to be sorry, Kyla. You had everything right. You just put in the wrong number. It was 8, not 16. The mass of an atom, we don't talk about it in pounds or kilograms because it's just so small. So we base everything off of something called carbon-12, which we'll talk about later. But we just base everything off of an atom of carbon. And protons and neutrons have a mass. If you want to think of it in kind of like pounds, is 1. If I have 1 proton, I have a mass of 1. If I have 2 protons, I have a mass of 2. If I have 2 protons and a neutron together, that gives me 3. And I just keep on adding these things until I figure out exactly what the mass is. So for oxygen, it has a mass of 16. Down at the bottom of the oxygen atom here, it says 16. So that's how much it weighs. Now, I know oxygen is number 8 on the periodic table, which means it has 8 protons. The only things that make up the mass of an atom are protons and neutrons. So if it's 16, you know that 8 of those things have to be protons. So whatever's left is neutrons. So that's where we kind of ended up. Did that clarify anything, Costin, or did it just make it more confusing? I know I used a lot of the kind of the vocabulary here, because I want to start to get into that habit. Okay, excellent. All right, so oxygen weighs 8 protons, plus another 8 neutrons. That's why at the bottom of the oxygen it says 16, because it has 8 protons, 8 neutrons down there. I could draw a picture if we wanted. Here's this little proton. There's 2 protons, 3 protons, 4 protons, 5 protons, 6 protons, 7 protons. Is that 7? 8 protons. All right, so there's 8 protons, and then I also have some neutrons in there. Let's draw those guys in. There's 1 neutron, 2 neutrons, 3. Oh boy. Have I mentioned how much I enjoy this computer? Try this again. 1, 2, 3, 4, 5, 6, 7, 8. All right, protons. Boom. Neutrons. 1, 2, 3, 4, 5, 6, 7, 8. All right, so if the black things are protons, the red things are neutrons. I have 8 protons, 8 neutrons. If I add them all up, I have 16. So that's the kind of the nucleus. So instead of drawing circles and dots and whatnot, I just kind of write it as 8 protons, 8 neutrons. Just count them out if you want. All right. Once we get this far, we've established what's in the middle. We need to figure out what we're doing in terms of electrons. So for the first, well, I don't want to say the first week or so, but for the first while, we're going to talk about atoms, and then we'll talk about ions, and they're a little bit different. So if we have 8 protons, that means in an atom, means that we have 8 electrons. So for all the questions that have to deal with atoms, if we have 8 positive charges, we have to have 8 negative charges. 8 electrons, 8 protons. They're going to be the same for a lot of this stuff. So if you recall back to the rules, and Eric helped us out, he said the first shell has 2 electrons in it. So let's draw on those 2 electrons. I'm going to draw them as dots. There's 1 electron. There's 2 electrons. So that shell's full now. The first shell can only hold 2. Once you get 2, you got to go to the next shell. That first one's full at 2. The next shell can hold 8. I'll get to your question here in a second, Costin. The next shell can hold up to 8, but we only have 8 electrons to begin with, and we've used 2 of them. So the next shell, although it can hold 8, we only have room, or we only have 6. Like we've used them all up, essentially. So the next shell can hold 1, 2, 3, 4, 5, 6. So 2 electrons in the first shell is 1, 2, and then the next shell has 6. 6 and 2 together gives us 8. We know it has 8 electrons in total. So because the first shell holds only 2, once we filled it up, we go to the next shell. That shell can hold up to 8, but oxygen only has 6 left, so we draw them in. Does it matter where they go? Could I have put these 2 over here? Yep, that's fine. They don't have to be there. It could look like that if you wanted. I usually kind of work clockwise from the top. Naturally, electrons will form pairs, and that's kind of, it'll become more important. You could just draw them as dots anywhere on that circle, but it's just kind of nice in terms of counting to just see them paired up, because people can count by twos really quickly, and it's just really quick. If I had drawn that second shell like this, I had 1, 2, 3, 4, 5, 6. I could have done that. There's nothing wrong with that. But if you're trying to figure out if you did it right or wrong, you're trying to count them, you literally, like, physically have to go through and count like 1, 2, 3, 4, 5. That's just a lot of work compared to just looking at 2 dots, 2 dots, 2 dots. Just easy to tell that that's 6 right away. So that's kind of why we pair them off, because they are naturally paired off, and then it's just easier to see them and visualize it that way. And that's it. That's what a Bohr diagram is going to look like for oxygen. There's nothing else to do. But to get back to your question, Costin, there's that -2 in the top corner. I believe this is what you're referring to up here, this -2. What does that mean? Well, atoms sometimes want to become really stable. And in order to become stable, they're going to, kind of gain and lose electrons and kind of trade them with people that are nearby. And when oxygen has the chance, naturally in nature, it'll actually steal 2 electrons from things nearby. And it'll have an overall charge of -2 to become stable. So the charges that you see in the top right corners of not all of them, but most of them have charges. That just means it's kind of the stable version of oxygen. We call it the ion. And in the case of oxygen, it wants to gain 2 more electrons. And we'll talk a little bit more about that here in a minute. It wants to gain 2 electrons to become stable. And there's more to it than that, but for now, we're not going to worry about any of the charges for the next few minutes until we jump into the ion section. All right, where did we leave off? So we talked about the rules. We tried to do a Bohr model of oxygen. What about the other 8 that makes up 16? In terms of that Bohr model, Costin, we're done there. So in the middle here, we had these 8 protons and 8 neutrons. Together, that gives us the 16. 8 p's and 8 n's is the 16. That's where the 16 comes from. 8 protons plus the 8 neutrons, we add those together, we get 16. But when we talk about electrons and protons are going to balance out. So if we have 8 protons, we'll have 8 electrons. Atoms want to be stable. They want to have the same number of positive charges as negative charges to become stable. I mean, for a lot of us, we probably haven't seen this stuff for, possibly over a year, possibly 2 years. So, Costin, I appreciate your questions. Likely other people are kind of going through the same thing, so don't feel like you're the only one. We're gonna just jump into ions right away. You know what I might do is this. We're going to just jump right out of here, and I'm just going to go into the learning guide. Sorry, wrong one. The learning guide has some Bohr model type stuff in it. Maybe we should do a few more examples. That'll probably be helpful. So going through the notes, we went through this stuff, kind of jumped past the ions. Then we talked about Bohr diagrams. And if we go even further, all right, so this is on page, you can correct me if I'm wrong on this, but page 9 of your learning guide, there are 2 examples here, boron and aluminum. Maybe we'll go through these together and then we'll, it's on page 10 of yours, Costin. Is that everybody else on page 10? Hopefully you can figure out where it is, but write the number of protons, neutrons in the inside. Yep. Okay. So let's maybe do boron together, and then I'll let you guys do aluminum on your own, and we'll just see kind of how we end up. So the middle, we write protons and neutrons, and then we have the shells to kind of fill from there. So boron, we have to find, first things, find boron on the periodic table. Now, I will stress this a lot. When you guys write your midterm exam, when you write your Unit 4 test, when you write your final exam, you're gonna have to, look up things on the periodic table. Now, in class, I'm always gonna look it up for you, but it is really, really important that you are trying to find these elements yourself. I'm not gonna say, hey, memorize the periodic table, but the more you use it, the more often the elements just kind of stick into your mind where they are. And it'll save you a ton of time. Literally, like in a provincial exam, if you're quick, you guys don't have the provincial exam anymore, but if you're quick at finding elements, it'll probably save you 10, 15 minutes over the course of an entire test. I'm not even exaggerating. If you have to spend 30 seconds trying to find boron on the periodic table, and you do that for 10, 15 questions, 15, 20 elements on a test, that's going to add up real quick. 30 seconds an element, times 10, 20, 30 times looking for these elements. So when we find elements, it's really important that you are able to just know where boron is. You should know where boron is in general, and then you kind of hone in on it a little bit faster. So hopefully you can find boron. I'll give you a second to find it. Maybe somebody wants to put the atomic number into chat once they find it. There we go. Thank you, Leeds. That'll help out a few people possibly. So the atomic number in the left corner, boron's 5 on the periodic table. So if it is number 5 on the periodic table, that's how many protons it has. Just that simple. The atomic number and the number of protons are the same thing. So that's a 5. All right, so we found the atomic number, which is the number of protons. The number of neutrons is the one we have to do a little bit of math, a little subtraction. So if we look at boron, it has a mass of, I believe it's 10. 10.8. I'm just going to bring up a bigger one here so I can see it. Yeah, 10.8. So when we have the mass of boron right next to my head here, it's 10.8. We always just round. So if it was 10.8, we're going to round it up to 11. If it was 10.4, we'd round it down to 10. You can see that some of them are exact, and then when you get into the middle of the periodic table, into these kind of transition metals, the things get kind of weird. You get 55.8 for iron, which is going to round up to 56. And then you have something like copper 63.5, we're going to round that to 64. And then zinc 65.4, we're going to round that to 65. We'll talk about why these numbers aren't exact in Chapter 7, Unit 7. So for now, we're just going to round them. So boron has a mass of 10.8. We're going to round that up to 11. We'll call that 11. And that just means it weighs 11. And we know already that 5 of its weights are protons. 5 of the thing that makes up boron is protons. So if we have a total mass of 11, and 5 of those things are our protons, what's left? Well, that must be neutrons, because those are the only 2 things that give us mass in terms of our element. All right, so the atomic mass, so we had 5 protons. The mass, in this case, is 11, which is protons and neutrons added together. So if we want to figure out the number of neutrons, we're going to take that 11, subtract the protons, and we're going to end up with 6. All right. So we have 5 protons, we have 6 neutrons. That's kind of the first stage of our Bohr model here. We figured out what the nucleus of this fellow looks like. Now we need to figure out electrons. Now for atoms, the number of protons is going to be the same as the number of electrons. The number of positive charges is going to be the same as the negative charges. So if we have 5 protons, we're going to have 5 electrons. They want to be neutral. You want to have a balance between positive charges and negative charges. All right, so let's draw them in. First shell can hold a maximum of 2. We have 5 in total, so 2 are going to go in the first shell. I'm going to use this as my first shell. This darker shell you could use if you wanted, but I think that's just trying to denote the nucleus, and then the first shell is the first dotted line. It doesn't matter. As long as your first ring, wherever you choose that to be, has 2. Okay, so 2 in the first shell, and then we have to go to the next shell. That can hold a maximum of 8, but we've only got 3 left. Now, I'm going to go kind of clockwise here. I'm going to go 1, 2, 3. Could I have put these together like this, like 1, 2, and then 3? Sure, I could have done that. Basically what's going to happen is they're going to kind of hang out by themselves until that you get to the 4th one, and then after 4 they're going to start to pair up. So how many blue dots do I have? 2 in the first shell, 3 in the second shell. It's a total of 5. We had 5 positive charges. We have 5 negative charges. So 5 protons positive, 5 electrons are negative. I'm not going to take off marks. Nobody's going to question it if you put the dots together. I've even seen stuff like this. Students will do like 3 right there all together. Technically that's just terrible, but is there 3 electrons in that second shell? Sure. Like, I'm not going to nitpick it. You understand the rules. I mean, they should probably be spread out, but I'm not going to harp on you too bad for that sort of thing. But as long as you have 3 electrons in that second shell, we're good to go. And you'll notice on the quizzes and things in the course, you'll see that the dots are spaced out until you get to 5, and they start to pair off. It's just kind of how these things look. I want you guys to do aluminum here, and then I'll do it with you after. And I'd like you guys to do aluminum. So I'll even help you find aluminum on the periodic table. Aluminum's kind of a funny one on the periodic table. It's kind of hiding. What's going on here? Why is that cut off? That's weird. Oh, that looks better. Mr. Ross is playing tricks on me. Aluminum, here she is right here, number 13 on the periodic table. There we go. Kind of just hides in that corner by itself on the staircase. All right. We're going to ignore the charge for now. See if you guys can draw that Bohr model. Protons and neutrons in the middle. Electrons around the outside. 288. Thank you, Eric, for throwing that number in. And see how we do. Brilliant, Kyla. Thank you. All right. Give you guys another second. I'll probably just end after this today. While you guys are drawing dots and subtracting numbers, super duper important that you guys are honest with yourselves at this point in the sort of chemistry unit. How much of this do you remember from previous years? Do you remember some of it, all of it? Are you kind of drawing blanks with things like atomic mass, atomic number, finding number of protons? These are things that you should have learned in the past. They should be like kind of ingrained in your brain sort of thing. So if you remember some of it, that's great. If you remember all of it, that's even better. But if you don't recall any of it, like it's possible that you just didn't learn this when you were in grade, whatever, 7, 8, 9, whenever you first saw it. You need to, do some review and, practice this stuff, because if you're struggling now, when you get, like 3 classes, 4 classes down the road, it's just going to be absolutely overwhelming for you. So at this point, you really got to be honest with yourself. If you're really struggling with these concepts, things that you likely have seen in the past, then you need to kind of go back and review. And we'll look at where you can do that here in a second. Let's first get this aluminum out of the way, and then we'll look at where you can do a little bit of review. All right, so aluminum's number 13 on the periodic table. That means it has 13 protons. Brilliant. The second thing we need to figure out is the neutrons. And we know the mass was 27. 13 of those things are protons. So if we go 27 minus 13, we're going to end up with 14. So we have 14 neutrons. Brilliant. All right. If we have 13 protons, that means we're going to have 13 electrons. The number of protons and the electrons, for now, are always going to be the same. So we start drawing them in. First shell holds a maximum of 2. So I'm going to put those together. First shell, 2. The next shell can hold a maximum of 8. So there's 1, 2, 3, 4, 5, 6, 7. All right. So the 2 and the 8 together have given us 10. And we know we have 13, so we have 3 left. So there's 1, 2, and 3. Oh, man. All right, so 2 and 8 is 10, 11, 12, 13. So we have 13 protons, 13 blue dots. Remember, the shells will hold 2 in the first shell, 8 in the second shell, 8 in the third shell. Sometimes you'll see questions that get into the fourth shell, but they'll never get past 2 or 3 things in that fourth shell. So we don't usually do Bohr models of things that big, because it doesn't really make sense to do that next row on the periodic table. So we'll just kind of, if you have to go into the the third shell, then just draw dots with reckless abandon and don't worry about it. It doesn't come up too often, but it will from time to time. All right, so there you have it. That's Bohr model stuff. The next question, I believe, nitrogen and phosphorus. You should attempt nitrogen and phosphorus on your own. We'll call that homework, if you will. I'll go through those with you next day. If you are struggling with the stuff, and maybe if you just want to review it, a lot of you have kind of expressed that you're remembering some of it, but some of it's kind of a bit foggy. When you go to the course, there's this kind of a build an atom practice kind of built right into the course here. So this is in Unit 2. There's a bunch of kind of different little, I don't want to call them games, but I don't know what to call them, simulations and whatnot, where you can just build atoms. So if I have 1 proton, I'm hydrogen. If I have another proton. You just kind of drag them and drop them over. Another proton, boom, helium. 3 protons, what am I? I'm lithium. And you can just kind of add stuff into the middle and, you know, drag and drop electrons. Kind of like an interactive Bohr model type thing. You can try to add a 3rd electron to that shell, but it won't work. And then you can add another electron, you get beryllium, or sorry, another proton. The electrons here are going to be spaced out kind of evenly, so you can go through that. You might want to click this stable, unstable, and you can see if you can make them stable or how to make them stable. So that's kind of a build an atom sort of thing. You can look at net charge if you want, you can look at mass, all that stuff's there. So it shows you where it is on the periodic table. Just kind of a fun way to go through and look at these things. You can look at it in terms of the symbol on the, down at the bottom, there's a choice for the symbol here. So you can add protons and a neutron, and it shows you what the symbol would look like on the periodic table. And then there's a game where you can just go through and, you know, do all sorts of different things. It kind of just quizzes you as to what goes where and whatnot. Atomic mass, atomic number, you can check, see your answers are right or wrong. So instead of just kind of doing work by hand, you might want to go through and just play around with that for, you know, 10 minutes or whatnot. Kind of be a bit of a refresher, hopefully. So does anybody have any questions in general at this point? I know this chemistry stuff is overwhelming once we really get into it. Not to say that students don't, you know, fully master it. I've had students get 100% on the Science10 at provincial exam before. It's not impossible stuff. It just, if you struggle at the beginning, you're going to struggle all the way through. So it's really important that you kind of really get a good grasp of things at the beginning. As we move forward, it'll be, you know, pretty straightforward. So I like to spend a lot of time doing the chemistry stuff. We'll go slow through it. I want to keep as many of you with me as possible. That being said, those of you who are still struggling through the units 1, 2, 3, and unit 10 from before the break, if you are trying to do that stuff while trying to do unit 4 at the same time, I don't want to say you have no hope, but you are going to just find this just overwhelming, absolutely overwhelming. So while we're at the very beginning of unit 4, if you are still working through the unit 10 material or previous to that, you just got to get it out of the way. You got to get it done. I would recommend I always want you to finish everything, but if you aren't done that stuff, and it doesn't look like it's going to get done, if you want to start fresh with this chemistry stuff, I would strongly recommend that. Because units 4, 5, 6, let's just take a really good look at exactly what chemistry is here. I always forget which numbers or which units. So unit 4 is kind of balancing. Unit 5 is, I believe, acids and bases, which is more chemistry, types of substances, salts, organics, inorganics. Unit 6, types of reactions. And then unit 7 is radioactivity. So units 4, 5, 6, and 7 all have to do with the stuff we're learning today. And it builds. It's not like when we talk about biology where we start talking about a biome. We're like, okay, let's talk about the permanent ice biome. And then we're talking about eutrophication and the nitrogen cycle. Well, they're kind of related, but you didn't have to know what a biome was to learn about the nitrogen cycle. They're kind of separated. In chemistry, everything from units 4 through 7 requires you to know what the atomic number is, what the mass number is, how to find protons, what an ion is, what an atom is. It all builds. I can't stress this enough. If you're unsure of what's going on in unit 4, you're going to be unsure in unit 7. So if you can master unit 4, then unit 5 will be easy, unit 6 will be easy, unit 7 will be easy. So there you go. Hopefully that's the last spiel I have to make. If you haven't finished unit 10 yet, get on it. We're running out of time. This unit 4 stuff is super important moving forward. So there you go. Thanks for sticking around with me today. We're back on, We're back on Thursday at 9 o'clock again for an hour or a double block, so we'll get a ton of this stuff done next day. Friday is golf, which is always fun. Get outside, go to the driving range. You don't have to be good. We get kind of lessons. You take turns. It's kind of social, and it's not like a PGA event. It's just kind of go out and hit some golf balls. Hit some golf balls badly, I guess I should say. That's my style of golf. So if you haven't come out to a field trip in a while, golf is a great, easy one. It's a lifetime sport. People play golf. Like my grandfather played golf into his 80s, had all sorts of physical disabilities, but he golfed his whole life. It's a good sort of social thing as well. So that'd be awesome to see you guys out to golf on Friday. So that's it for now. Go through those next 2 bore models in your learning guide and have those done for next day. We'll talk about them in class. And if you guys run into any problems, just send me a message in Moodle and we'll get back to you. Thanks. See you on Thursday.